Hello everyone, welcome to the Mercury Virtual. Hope you are doing good. Today I am going to continue with chapter number 4, that is processor architecture. In the yesterday's class we have discussed one topic, that is SCL, hardware control language. Today I am going to continue with your next topic, that is Y86 implementation. So let's take a quick review what we have covered in the yesterday's class. In the yesterday's class, we have discussed about chapter number 4, that is digital logic design. Digital logic design. So digital logic design is a system in which we compare or we are using how computers are built, or what is the designing of the computer. Means what are the inputs, what are the outputs. We have discussed about various inputs and the various output operations. This is, as a digital design engineer, you may assist in developing cell phones. Means if you have knowledge of the designing of the computer, then you may assist, or one can assist in developing the cell phones, computers and related personal electronic devices. Continue reading to find out what training can develop scaling functions. Then we have also talked about the Boolean algebra. This is the most important part in designing, that is how we can implement the arithmetic operations with the help of Boolean number, that is zeros and ones. So there are two parts. One is algebra, one is Boolean. Boolean means zeros and ones. Algebra means performing the operations. That may be arithmetic operations, that may be logical operations on the input. So Boolean algebra means performing the arithmetic or logical operations on the Boolean values, that is zeros and ones. That is known as Boolean algebra. This takes two values, that is zeros and ones. As I told you, there are three basic functions. These are the basic functions, but not the other functions. These are the basic functions, that is AND, or NOT. Then any Boolean function can be constructed from these three. Means these are the three basic functions, and we can construct any number of values, any number of inputs, any number of functions from these three numbers. And this is a table for AND. We have discussed OR and NOT. Then we have discussed about some loads that is available, means some terms, some conditions that is available in Boolean algebra. One is your identity, dominance, commutative, associative, distributive, De Morgan. This is most important, that is plus becomes a into. Plus is your OR operation, into multiply is your AND operation. So whenever we perform, or whenever we use De Morgan's law, then the addition, that is OR operation, is converted into the AND operation, and the AND operation is converted into the OR operation. That is your De Morgan's theorem or De Morgan's law. That is, OR operation is converted into the AND operation, and the AND operation is converted into the OR operation. Then we also discuss about the Boolean expressions, that is how we can represent the Boolean expressions. That may be OR, that may be AND. And NOT is represented by a prime number, that is A dash or A dash, hyphen or A dash. These are the multiple examples we have discussed. These are the basic logical case that we discussed. This is a shape for AND gate, this is a shape for OR gate, this is a shape for NOT gate. This is the exclusive OR function. This is exclusive OR, that is finding the OR and then there is the exclusive. The main condition is that if both the inputs are 1, then always the output is 0. But in AND operation, both the conditions must be true, that is 1, then the output is true, otherwise the output is 0. And in OR operation, any one of the input is either 1 or true, then the output is true, otherwise the output is 0. So there are AND or NOT. First of all, AND, that means multiplication. Both the values are true, then always the value output is true, otherwise the output is false. In OR operation, if any one of the input is true, then the output is true. In NOT operation, just inverse of the or inverting the bits. 0 becomes 1 and the 1 becomes 0. Then exclusive OR, the condition is that if both the inputs are 1, then the output is 0. That is your exclusive OR function. These are the multiple additional logic gates. These are the basic logic gates. Logic means zeros or ones for finding the inputs and the outputs. These are basic logic gates, that is AND or NOT. And these are the, this is the exclusive. These are the additional logic symbol, that is NAND. Means finding the NOT of AND, as the name advises, NAND. That is AND of NOT or NOT of AND. That is finding the NOT operation on the AND operation. Then NOT, that is finding the OR operation and then inverting the bits, that is your NOT. In the same way, there is a buffer, there is a XNOR. That is finding the NOR and then XOR. That is, if there are two inputs, that is 1, then the output is 0. So that's all for yesterday's session. Now today I am going to continue with your next topic, that is sequential Y86 implementation. Today's system is so hang. We have discussed about the SCL also, that is hardware control language. We have discussed about the combinational circuit, that is how one input is given and how one output is generated. These are the multiple examples, and we have also discussed how to create the combinational logic. Means how to use the AND gate, NOT gate and the OR gate. These are the multiplexer, that is if there are n number of inputs but the output is only 1, that is known as multiplexer. In the same way, demultiplexer is if there are so many outputs but the input is only 1. Means one input is given but there are so many outputs. In multiplexer, there are multiple inputs but the output is only 1. Then word level combinational circuit, that is how to do the word by word combinational circuit by using the bit equal or the equal bit. These are the example in C language, that is using the SCL. Then we also discuss what is memory and how do we use the clock. That is how we can increment with the help of clock in assembly language or in Y86 architecture. Now, next is your sequential Y86 implementation. This is your today's topic. That is sequential Y86 implementation. This says, note that we have the components required to implement a Y86 processor. As we discussed about the Y86, so now it's a time to implement the Y86 processor. At the first step, is that we describe a processor known as the SEQ, that is your sequential processor. So the Y86 processor is also known as SEQ, sequential processor. On each clock cycle, SQ performs all the steps required to process a complete instruction. This would require a very long cycle time, however, and so the clock rate will be unacceptably low. So this says whenever we use the multiple steps to complete execution, that requires a long time or the long cycle or the low cycle time. So the clock rate is very low. Our purpose to develop or in developing SQ is to provide a first step towards ultimate goals of implementing an efficient processor. Then how to organize the processing into the stages, that is how to perform or how to make the different operations in assembly language by using the Y86 processor. Now let's see with the help of some slides. There is a slide here. So chapter number 4 continue, that is processor architecture. There is a sequential Y86 implementation. Now the today's topic is divided into three parts: Y86 introduction, Y86 instruction set architecture, Y86 implementation. First is Y86 introduction. First of all, what is Y86? It is a subset of the IA32. What is IA32? That is Intel Architecture 32. That is of 32 bits. That is known as IA. So it is a subset, means a new version of the IA32. The IA32 ISA has too many instructions with an overly complicated encoding, too many addressing modes, efficiency over simplicity. So we use a simplified version that is invented by the textbooks authors as a teaching tool. It has 8 general purpose 32-bit registers. So Y86 is of 32-bit register and it contains 8 general purpose 32-bit registers. There is one PC, that is program counter, for taking the address for the next instruction. There are 3 condition codes also, 0F, that is 0 forward, single forward or overflow, that is sign flow, zero flow and the overflow. There are 12 types of instructions. So this is a Y86. Introduction is just simple because I have already discussed about the Y86 in detail. So it contains 8 general purpose 32 registers, 1 PC, 3 condition codes, 12 types of instructions. Then next topic is your Y86 ISA, that is instruction set architecture. So as I said, there are 8 registers of 32 bits each. So this is 8 registers. This is 0, 1, 2, 3, 4, 5, 6, 7. There are 8 registers starting with 0, ending with 7. That is EAX, ECX, EDX, EBX, ESP, EBP, ESI, EDI. So there are 8 registers. Instruction that only need one register uses 8 or F for the second register. Then next point says percentage ESP is used as the stack pointer. As the name advises, stack pointer, ESP, stack pointer. And the memory contains 2 32 bits. All the data accesses, load or store the 32-bit word address. These are the multiple instruction types that are used in IA32. What are the instructions type? First one is your register memory transfer. Means how we can transfer the content from the register to the memory, from the memory to the register, or from memory to memory, or from register to register. That is done by the multiple instruction, and that comes under the topic instruction types, and the first one is memory or register transfer. So the first instruction is RMMOVL RABRB. So this is from register to the variable or register to the memory. So this is used for transferring the data to the memory, that is register to the memory and store the output in the memory, that is DRB. M4 D plus RRB RA. This is also the same version of this one. Example, RM move L EDX. This is a register and this is your memory. So move the content of the register to the memory, this one memory, and store the output in the memory. Then next one is your MR move L. That is move the operator or move the content of the memory to the register. This is said, this is the content of the register, content of the memory is moved to the register. That is M, this is memory, move the content to the register. This is R, move the content to the memory. This is the example, MR move L EDX, or this is the memory, then register. Next instruction types are, other instruction type or other data transfer instructions are RM, move L, RA, RB, that is moving the content of one register and storing the content in another register. Then IR, move L, VRW, that is V is a variable storing the output of V to the RB, that is storing from one variable to the register, that is your also one of the instructions. Then next instructions are arithmetic instructions. As I told you, there are so many arithmetic as well as a logical instruction. So the first one is add L, RA, RB, that is for adding the registers or for adding the contents of the registers, we use add L, RA, RB, that is register of A and register of B. Then subtract L, RA, RB. Then finding the AND operation of the RA and the RB means finding the AND operation between the register A and the register B. Then XOR RA, RB, that is finding the XOR operation between the registers RA and the RB. Then multiply the RA and the RB means multiply the registers, that is RA and the RB. This is the explanation. This is used for addition. This is used for subtraction. This is used for finding the AND operation. This is used for finding the XOR operation between the contents of the register. This is used for multiply the contents, that is multiply the registers, that is RA and the RB. Then dividing the registers, that is RB and the RA. Then finding the modulus. As I told you, there is a new version, that is how to find the remainder by using the modulus operator. So whenever we find modulus operator, this is one of the arithmetic instruction that is available. So finding the mode between the register is also one of the instructions. Next instruction is your unconditional jump, means jumping to the destination. That is from jumping destination to the PC. That is your JNP destination. Next, conditional jump, that is JLE, destination if the last result is greater than equals to 0. JL if the last result is less than 0. JE if the last result is equals to 0. This is used for last result, less than equals to, not equals to, greater equals to, and greater than. So this LE is used for less than equals to, L is used for less than, E is used for equals to, NE is used for not equals to, GE is used for greater than equals to, and G is used for greater than. So these are the multiple conditional jumping operators, conditional jumping instruction that is available in Y86 processor. This is your unconditional, this is your conditional jump. Next instruction that is available in Y86 are conditional moves. That is how to move the instruction conditionally based on the condition. How to move. Till now we have covered about the move instruction. That is not condition based. That is unconditionally. But now there is a condition based instruction that is on the basis of conditions how we can move the instruction from one register to another, one memory to another, memory to register, or from register to memory. So the first one is C move, means move the instructions if there is a less than or equals to, means there is a condition also and movement also. So move when there is a less than or equals to number. This is C move MOV LE, that is less than equals to. Then C move L, that is move the instruction if there is a less than value. This is less than and equals to 0. This is only less than 0. Then move the instructions if the values are equal, that is E. Then move the instructions if the value is not equal. This is not equal, not equals to 0. Then move the instruction if the value is greater than or equals to 0. Then move the instructions if the values is greater than 0. This is greater than equals to, this is greater than, this is not equals to, this is equals to, and this is less than, equals to. These are the multiple conditional movement, conditional instruction that is available in Y86 implementation. Then next one is your runtime stack. That is how we are using or how we use the runtime stack. So this is your stack implementation between the IA32 and the Y86. This is the caller's local data, that is your local data, argument 1, argument 2, argument 3, return address. These are the instructions that is stored in the stack, that is based on the LIFO, that is last in, first out. Then next is percentage EBP, that is saved caller, percentage EBP. Then next one is your local data. Next ESP, that is used for stack pointer, that is also stored or that is used for the local data also. This is the address, that is 0 into 1000, 0 into 101C. This is your local data, callers. This is your stack pointer that also contains the address, and these are the multiple arguments, return addresses, local data. Next point says stack grows towards lower addresses, means they are coming or it is coming or it moves from the up to the down. That is first of all this one. Then argument 1, take argument 2, take argument 3, take return address, save the caller's EBP, then local data, and then using the stack pointer. Next instruction type is known as procedure calls and return support. Means how to return the process or how to call the procedure. Procedure means a sub-program or the one function of the program, that is your sub-program. Procedure calls and return support, that is your next instruction. There are multiple instructions available like call, CALL, destination, that is call the destination and return the value, that is known as CALL, DEST. That there is a return value, that is returning the value from the memory to the PC. Then push LR means push, inserting the operations of the register, that is inserting the operations or inserting the value into the register. Then pop L means retrieving the instruction from the register, that is RA. Push LRA means inserting the instruction into the RA register. Other instructions are hold and NOP, that is stop executing the instruction, that is done by the hold, and NOP is of no use, that is no usage of instructions. This is a C example. Next is your C example, that is how we are using the C example and how we can implement the Y86 with the help of C example. This is a C example. Now let's see. First of all, take the array variable, that is start. This is the array variable. How I know this is the array variable? So there is a subscript or there is a bracket, square bracket along with the name of the variable, that is start square bracket. So start is an array variable that takes integer values. And there are multiple values stored in a start operator or the start array, that is 4, 7, 8, 9, 12, 11. So there are 6 values stored in the start array. Then using the one function, that is using one procedure, that is int sum underscore function. So this is the name of the function and the return type is int. As I told you, there is a function or there is a syntax. This is known as return type, that is it returns the value that is of integer type, that is in digital format or that is in whole number. So this is your return type. This is your function name. This is your function name. This is your array name. Array name, these are the elements. Then next, int sum equals to 0, that is taking the one variable or taking one variable, that is sum. This is the definition of this function. The function name is sum function parenthesis. Then this is the explanation of this function, that is sum equals to 0. That is sum has a value 0. Sum is the variable that stores the value 0. Count is also another variable that takes the value 6. So there are two variables, sum and the count. Sum takes 0 and the count takes 6. Next, using the pointer. The pointer name is str, that contains the start output, that is whatever the start output that's stored in the str, or if I say this is also correct, that is str is the pointer variable that stores the address of the start variable, because pointer is a variable that stores the address. So str is the pointer variable that stores the address of another variable. Which variable? That is the start variable. So it stores the value, or it stores the address of the start array. That is, it stores the address of 4, 7, 8, 9, 12, 11. So it stores the addresses of all the elements. Then next, using the while loop. While loop, first of all, check the condition. The condition is that while count means it contains 6. So it starts from 0 and it ends with 6. That is, it iterates with the 7 element. It iterates with the 7 operations. So it starts with 0 and ending with the 6. So it contains 6 values, or it starts with 0 and ending with the 6, that is equals to 6. So there are 7 operations. Sum plus equals to str. Adding the values into the sum, or adding the values of sum and then give the str, or it contains, or it stores the address of the str. Then str plus plus means incrementing the pointer variable, or incrementing the addresses of the pointer. If I take one address, then increment by the another address, or increment by the another variable, another data type. Suppose if I've taken int pointer str, so increment by the 22 bytes. If str address has 045, so increment by 047. So why it is incremented by 22 bytes? Because int takes 2 bytes, so it is incremented by the 2 bytes. Then next is your count minus minus, that is decrementing the values of count whenever it gives the number, or whenever it stores the number. That is count minus minus, because count has a value 6, then it becomes 5, 4, 3, 2, 1. That is your count. And then at last return the sum, that is return the value of the sum. This is your definition, starting with this, ending with this, and then this is your main function that ends with this. Which main function? That starts with this curly brace and ends with this curly brace. This is the definition of the while loop, and this is the whole definition that starts with this and ends with this. This is your C example. Next, how to compile to assembly by GCC 4.4.3. So this is how we can compile in assembly language. First of all, uses the sum function, the same sum function. Move L, first of all move the pointer, the same syntax. This is int pointer str equals to start. That is, start is the array that has an address, that address is stored by the str pointer variable. Then finding the XOR operation on the EAX and the percentage EAX, that is sum equals to 0, means initializing the value of sum to the 0. Then this is your L2, that is how to add the operations. These are the multiple steps. First of all, use the add L, add Q, compare, then JNE.L2, because this is the L2, then JNE means jump to the L2, then repeat, and then return. Why it is jump to the L2 again? Because it is a looping, and there are multiple iterations. So move to the L2, again move to the L2, again move to the L2. That is for jumping, and then this is repeat, there is a return output. Then how to write or how to return for the Y86, that is first of all, post 0 into 100 means first of all defining the variable, that is position, or defining the position, that is 0 into 100. There is a sum function, same. move the values from one register to the another register, that is moving the values from EDX to the A, then moving the contents from EDX to the EAX, that is finding the operations of XOR, that is finding the XOR operation between the EAX, that is XOR EAX percentage EAX, then again using the L2 MR move, again move the result and then add the result. This is used for moving and then add. This is used for moving and then add. This is used for moving and then compare. This is used for comparison. Then subtract LEDX EBX, then jump to the L2 and then return the value. This is the same format as the assembly language. There is little bit difference, that is move words are adding or move instructions are added, that is IR move, MR move, IR move. Next is your how to implement the Y86. But before that, let's take your quick review of your book. This is your book. First of all, it organizes the processes into multiple stages. Now, I have discussed this one. These are the multiple stages. This is the multiple stages. First of all, this is Y86 implementation. I am coming to the stages, that is it modularizes or it divides by dividing the instruction execution into the 6 stages. These are 6 stages that is most important for the Y86 implementation. Now let's see one by one about the stages, about the instruction that is executed into the 6 stages. The first stage is fetch. As the name advises, fetch means reading the instructions or fetching the instructions from the register or from the memory. That is known as fetch. That is read instructions and decides on new PC value. That is read the instructions from the memory or from the registers and decide on the new PC value. Then next one is your decode. After fetching the instruction, read from the register. That is, first of all, the first target is that fetching the value. Then next one is that read from the register. That is known as decoding. So fetching means fetching the data that is from memory, and then decoding means read from the registers only. That is RAX, ESP, EBX, ESI. Then next part is your execute. So till now we have covered only fetching, that is retrieving, and then decode, that is read from the register by changing the format. Then next part is your execute, that is execution of the instructions, that uses the ALU. How to execute? Uses the ALU, that is arithmetic and logical unit, or uses the ALU to perform the computation or to perform the calculation. So the third point is performing the operations like arithmetic operations, logical operations with the help of ALU to execute the value. Then next is your memory, that is store the output or store the result or store the given data into the memory. That is read data from and write data to the memory. Means also fetching the data from the memory as well as writing, means storing the data into the memory. That is done by the next stage, that is your memory. Then write back means writing the result or storing the result into the register or registers. If there is only one value, then it is stored in one register. If there are multiple values, then it is stored in multiple registers. Then next one is your PC update, means if there is any update in the PC, that is stored in the new PC value. PC means program counter. So it is stored in the new PC value or to the next instruction, that is carry forward, or that address is stored in the PC, that is your program counter. So these are the 6 stages. First one is fetch, decode, execute, memory, write back, PC update. So these are the 6 stages. Now let's see with the help of the book. So these are, in this says in general, processing an instruction involves a number of operations, we organize them in a sequence of stages. So we organize them into the stages, attempting to make all instructions follow a uniform sequence. I mean, there is no hard and fast rule that sorry, go to the that one, but it creates a sequence, that is, you follow these sequence so that operations can be done, or operations can be done in an organized manner. The following is an informal description of the stages and the operations performed within them. So these are the multiple instructions, or these are the multiple stages that is used to perform the operations on the instruction, or to perform the operation with the help of instruction. First one is your fetch. The fetch stage reads the byte of an instruction from the memory. As I told you, fetch is used to read the instruction from the memory using the program counter as the memory enter. So uses the PC, that is a program counter, as the memory enters. From the instruction, it extracts the 2-bit portion of the instruction specified by it, refers to as I code and the hyphen. Then next stage is a decode. So first fetch, then decode. The decode stage reads up to 2 operands from the register file. So it can execute, or it can read 2 operands from the register file, from the register, typically, or giving the values as the val1 and val2. Typically, it reads the register designated by the instruction field, that is RA and the RB. But for some instruction, it reads register ESP. So first one is your fetch, then decode, then execute. In the execute stage, the arithmetic and logical operation either perform the computation specified by the instruction, compute the effective address. So it performs multiple operations in execute stage. Either it performs the calculation, operation, stack pointer, increment, decrement, memory reference, anything that is done or that is used for execution, that is done by the ALU, and that comes under the phase, under the stage, that is execute. Next stage is your memory. The memory stage may write data to the memory. So that is used for writing and retrieving the data from the memory. That is known as memory. So this says the memory stage may write data to the memory, or it may read data from the memory. We also refer to the value read as val m, that is read the value from the memory, that is val m. Then write back, that is the write back stage, writes up to 2 results to the register file. It is mandatory that it writes the data, or it gives the data to the memory at the most 2 stages, or at the most 2 times. Or it may read the data from the memory. Then PC update, the PC is set to the address of the next instruction. That is your PC update. Next is the processor loops indefinitely performing these stages. So the processor loop performs all these 6 stages that is available for performing the operations efficiently and effectively. These are the multiple instruction sequences, that is IR move, subtraction, as I told you. There are multiple instructions which is discussed in this paragraph, like hold, arithmetic, add, sum, MULP. Then these are the multiple stages and these are the multiple operations. Fetch stage, OP1, RA1, RB, that is performing the operation between the RA and the RB. Then move the value from the RA and the RB. IR, move the value from the register to the variable B. This is used for fetch, decode, execute, memory, write back, PC, update. These are the same, and that is the explanation of the diagram or explanation of the table. These are the examples, what is the value of this one and how the PC executes this one. This is the computations in sequential implementation. There are multiple push operations, pop operations that is used in sequential circuits, that is used in multiple stages of execution, that is fetch, decode, execute, memory, write back, PC update. This is a push operation that is used for inserting the values. This is a pop operation that is used for retrieving the values. These are the multiple examples. This is the block diagram, that how it is maintained. First of all, data memory, ADA, data, val E, performing the operations. That is first of all write back, this is PC, memory, execute, this is decode, and then fetch. So this starts from this one. First of all, fetch operation, fetches the memory, then decode, that is executing or that is decoding from the register file, then execute with the help of ALU, arithmetic and logical unit, then storing the value or retrieving the data from the memory, that is execute, then memory or execution is done by the ALU, memory means storing the data, then write back, writing the value to the E or the M, there is a PC, that is your PC. So these are the again the stages, or these are the registers that is discussed with the help of diagrams. These are the multiple conventions. Hardware units are shown as light blue boxes. So these are the hardware units that is shown in the blue black boxes. These are the boxes. This is. So these are the multiple implementations part. Then control logic blocks are drawn as gray rounded rectangle. Right wire names are indicated in the white round boxes. Worldwide data connections are shown as medium lines. This is the explanation of the diagram. Byte and narrower data connections are shown as thin lines. Single byte connections are shown as dotted lines. So this is the diagram. There are multiple shapes like this one, thin dot line, arrows. This is your shaded line, or this is your shaded box with the gray shade. So these are the explanation of the diagram, that is figure 23. This is your next figure, that is your architecture for the memory, or this is the structure of the SEQ, that is sequential query or sequential circuit. Same operation, first of all fetch, then decode, then execute, then memory, then PC. Then SEQ timings, that is what is the timing or what are the requirements for the timing, at which time the data will be uploaded, at the which time the data will be retrieved from the memory. That is your SEQ timings. This says our implementation of SEQ consists of combinational logic and two forms of memory devices, that is clock registers and the random access memories. So timing is very crucial. As I told you, there is a clock that is used for implementation or incremented or decremented. This is the diagram how clock moves from one part to the another part. These are the two clocks that are used or executed by the SEQ. Then next is your SEQ stage implementation, that I will discuss after the break. So let's take 5 to 10 minutes break and then come back again, starting with Y86 implementation in detail. So let's take 5 to 10 minutes break and then come back. Let's start with your next topic, that is Y86 implementation. So let's start with the help of PPTs. How we can implement the Y86 ISA. So how we can implement? Using the registers, memory, ALU, PC, that is program counter. So we are using, or we use registers that is so many registers that is available in ISA, memory, primary memory, secondary memory, ALU. Then ALU, arithmetic and logical unit, that is used for arithmetic operations as well as logical operations. PC, that is used for program counter. So these are the requirements that we use while implementing the Y86 ISA. Then next point says all tied together using combinational circuit. Means there is a requirement of register, there is a requirement of memory, there is a requirement of ALU. Along with that, there is also a requirement for the combinational logic, combinational circuit, combinational gates, that is AND gate, OR gate, multiplexer. AND gates means there are multiple AND gates like NOT gate, AND gate, NAND gate, XOR gate, OR gate, exclusive OR gate, multiplexer, demultiplexer. There are so many combinational logic circuits that we discussed in yesterday's class that all are required for the implementation of Y86 ISA. Then next point, or the next question says, how do we describe the combinatorial logic? That is, the book uses the SCL, that is, we have discussed in the yesterday's class, that is SCL, hardware control language. We will use a Java implementation instead. Means either we can use the SCL, that is hardware control language, or either we can use the Java language for the implementation of Y86 ISA. So these are the multiple requirements, or these are the multiple things that we require for to implement ISA, Y86, or what are the methods, or what are the ways to describe the combinatorial logic. Then how to modularize, as I discussed, how to divide the instruction execution into the 6 phases. First one is fetch, decode, execute, memory, write back, PC update. Then this is an example of different stages. Like first one is your fetch. Example is that RM move RA DRB. That is moving the memory content from DRB to the RA. That is RM move L RA DRB. First one is your fetch. That is how to fetch the instruction. First one is I code I1 MPC. That is using the PC operator, using the program counter, then moving from program counter to the I code or I1. Then RARB, that is moving the instructions, or move the instructions from PC1 to the, or PC1 plus PC plus 1 memory to the another register, that is RA:RB. Next, moving the instruction from the memory or to the another memory, that is this memory, to the val variable or the value that is in C. Then this is first of all adding the values of PC. This is only the PC, means the program counter that stores the next instruction, that is stored by using the memory and stored in the I code. Then incrementing the PC's value, that is program counter, by 1 and stored in the next register. Then incrementing the PC's values by 2 or the PC value by 2 and then storing in the next variable, that is val C. Then incrementing the PC variable by 6 and then storing the next variable, that is value P. Then next one is your decode, that is how to decode the values. First of all, use the register RA and store the value in variable or value A. That is using the register that is known as RA and then store the value and store the output to the, or store the content of the RA to the value A. Then RRB, that is using the register RB and stores the register RB content to the value B. So first one is your fetch. This is used for fetch operations. Then these are used for decode operations. Then execute operation, means performing the execution with the use of ALU, that is adding the values of B and adding the value of C and store the output in E. That is, first of all add the value of B, add the value of C and store the output in the value E. This is fetch. Decode means inciting First of all, fetching the value from the memory, then decode means changing the code for the decodation, then execute with the help of ALU, then storing the output or the storing the value into the memory. That is next stage, that is your memory. That is val A, value A, stored in the next memory, stored in the memory, that is M4, value E. Then next part is your write back, that is write the operations. Then PC update, that is using the value 1 and that value will become the next PC instruction or the next PC, that is program counter. So now value P becomes the PC, that is the next instruction address, that is val P. These are the implementation details, means what are the implementation details that we require for the implementation of Y86. First one is read-write memory, that is memory.read address, NB bytes. That is using the memory, using the dot operator for fetching the memory, and there are two operands or there are two variable arguments inside the parenthesis. One is address, another one is NB. Then next one is your next operation or the next function is your MEM, that is memory.read integer. The function name is read integer, and how we can fetch by using the memory, that is read and the write memory. We can use both the memories, read memory as well as the write memory. So memory.read means finding the values or reading the values, and there are two variables. One is address, one is NB bytes. Then memory.read integer address, that is read the integer and the argument is address. Then mem.write integer means writing the integer and the arguments are two arguments, that is address and the value. So these are the read-write memory that is used for implementation of the Y86. Then read-write register file, that is what are the requirements or what we require for the implementation of the Y86. What are the register file that is required? One is register.read, one is used for reading the file, or one is used for reading the register, means reading the content of the register, and the next one is reg.write, that is register write. One register is used for writing the output. So one is used for reading and one is used for writing. So implementation also includes, implementation details also include the read-write memory and the read-write register file. Then these are the new registers or these are the additional registers that is required. Next one is the read-write stage register. So till now we have covered two things, that is read-write register and the read-write memory. Next one is the read-write stage register. Next register is the read-write stage register, that is fetched by using the s.name.read and then parenthesis. This is s.name.read. This is this is s.name.read input parenthesis or s.name.write. Means we can either use read or either use write. Means we can read the data from the stage register or we can write the data into the stage register. So that data can be read or the write from these syntaxes like s.name.read, s.name.write. Or we can use for the s.read or this one s.name.read input. This is for write. For writing purpose we use s.name.write operation or the write function. Then this is the most important, stack includes. This is used for inclusive part, that is stack includes F, D, E and W. These are the multiple stages depending on which stage is used at the input. So these are the multiple input or the stages that is available for the stage register like F, D, E and W. We can use for the in Y86 implementation use either F, either D, either E, either M, either W. That is stored in the stage register, that is S. Next point says differences from the Y86 CPU from the book. there is a difference between the Y86 and the CPU. The first one point says the book describes a little endian CPU. The value 0 into 1234567 will be stored as 78563412. That is in the decreasing order, that is from the left to from the right to the left. First of all 7, then 8, then 5, then 6, then 3, 4, 1, 2. So it is the description, or it is the description of the CPU, that is described by the CPU how to implement the Y86 format. Next one is your next point says the simulator implement a big endian or big endian version, that is the value 0 into 1234568 will be stored as, will be written as 1234567. So the book implements, or the book describes the values from the left, from the right to the left, and the simulator defines the value from the left to the right. So first one is little endian CPU and the big endian version that is used by the simulator. Now let's see with the help of book. This is your book. This is your stage implementation. This says in this section we devise or we revise SCL description for the control logic blocks required to implement SEQ. That is, we are required SEQ, sequential, for description or for describing the SCL, that is hardware control language. Next point says a complete SCL description is given in the web-aside arch.SCL. So the complete description of the SEQ will be given in the next website, that is web-aside ARCH, that is architecture:SCL. Part of the SCL description of SEQ that we do not include here is a definition of different integers. So we may use multiple integers, or we may use different integers and the different signals as an argument. As I told you, we can use multiple signals, multiple arguments, multiple values for the SCL operation, that is for the hardware control language operations. These includes the name of the different hardware signals as well as the constant value for the different instruction codes, function code, register name, ALU operations, and the status codes. So this paragraph says there are multiple ways for implementation of the SQ. We are using the SCL, that is hardware control language, for implementing the SEQ. So this is the first stage is your first stage. As shown in figure 27, the first stage includes the instruction memory hardware. Now let's see. This is your figure 27. This is your SEQ fetch stage. 6 bytes are read from the instruction memory using the PC as a starting address. From these bytes, we generate the different instruction fields, the PC increment block computer signal, VAIP. So these are the multiple PCs, these are the multiple instruction, and this is known as the, and this is this diagram shows the fetch stage. That is how we can fetch the data from the memory or from the register. First of all, it is from the memory, that is PC increment with the use of VAIP. Instruction memory means fetching the data from the instruction memory, then split the data into the multiple parts, align the data into the multiple parts, then split the data into the I code and the I1, instruction valid, whether instructions are valid or not for the data operations, then need val C, that is need the value of C, need the registers or the register ID, these are the multiple registers ID, register code, that is I code, I1, RA, RB, value C. Then there is a need val C, that is need the value of C. So these are the fetch instruction that is used by the Y86 implementation or the Y86 fetch cycle. This paragraph. So this is a fetch cycle which I have discussed with the help of diagram. That is how we can fetch the data from the memory. One is instrd value. This is shows or described. Does this byte correspond to the legal Y86 implementation? Need register ID. Does this instruction includes a register specifier byte? Need VLSE. Does this instruction includes a constant word? These are the multiple instructions, multiple meaning of the instruction. One is INOP, that is code for no instruction, code for hold instruction. This is I. This is IRR move L, code for RR move L instruction. Simply use the I for the coding purpose. Then IIRMOVL, use the code for RMVOL. Then RMMOV, that is the code, this is the code. So these are used for coding purpose. Now, next one is your FNone, that is default function code. Then RESP, that is register ID for the register, that is ISP. Then RNone, that is indicates no register file access. Then adding the ALU, that is function for the addition operation. Then status code for the normal operation, status code for the address exception, then status code for the illegal instruction exceptions, then status code for the hold. So S is used for status code. There are different instructions, there are different registers like HLT, INS, ADR, AOK. These are the constant values used in SCL description. This is your diagram or this is your coding, that is how we can use or how we are using the Boolean register, that is whether the register have a strong ID in their registers or not. This is the coding part, this is the diagram as we discussed. Next is your decode and write back stages. Till now we have covered about the fetch stage. Next is your decode and the write back stages. Figure 28 shows about the decode. This is figure 28. Previous figure is fetch figure and the now is decode figure. That is how we can decode and how we can write back the data. So this is your I code, RARB registers. I code are used for instruction code. This is your destination M, source A, source B. So there are two destinations, that is F and M, and there are two sources, that is A and B. And then C and D, value 1, value B, value A, value B, value F, value E. So there are four values. This is the register file that contains DSC, DSM, source A, source B. That is destination and the source. And these are the values of the M and the E. This says the instruction fields are decoded to generate register identifier for four addresses, to read and the to write. These are the to read instruction and the to write instructions used by the register file. The values read from the register file become the signals val1 and val B. The two write back values, that is val E and the val M, serves as the data for the write, or serves as the data for the return purpose. This is the coding that is used by that is done in the assembly language. Next is your execution phase. Till now we have covered fetch, decode, write back. Next is your execution phase diagram. The execution includes the ALU, that is arithmetic and logical unit. The main operations are add, subtract, and exclusive OR on input ALU A and the ALU B. So this is val C, that is value C, val A, val B. This is set CC, condition codes, ALU. ALU function, conditions, icode, I1. These are the functions. So ALU contains the operations like AND, OR, NOR. First of all, add, addition, subtraction, AND operation, exclusive OR operation on the inputs, that is ALU A and the ALU B. This is your ALU functions using the CC, using the condition, set the CC value. ALU A means performing the ALU operations. Next, performing the ALU operations on the B. This is your coding for the coding that is done in the C language for the ALU or for the execution phase. This is your memory stage. This is your memory diagram. That is how we can store in the memory. This is your memory stage. So this is your memory that shows the data memory can either write or read memory values. The values read from memory forms a signal val n. This is your start, memory read, memory write. This is the instruction valid or not. This gives the error, data memory, memory address, memory data. This is the I code, value E, value A, value P. This is your memory stage. One is used for write operation, another one is used for read operations. PC update stage, last stage is your PC update stage. This is the coding for the PC update. Diagram for the PC update, simply use the I code and the PC program counter, CNT condition, val C, val M, DA, IP. Then how to survey the SEQ, that is how to use the SEQ values. This is the serving. Serving means how to use the SEQ value, that is sequential values. It is the very main thing is that there are 6 phases, there are 6 stages, that is fetch, decode, execute, memory, write back, and then at last update the value. So these are the multiple 6 values that is used with the SEQ. The only problem is that it is very or it is too slow. The clock must run slowly enough so that signal can propagate or the signal can propagate through all the stages, or signal can transform from all the stages within a single cycle. Means we can execute one cycle and the multiple problems or the multiple SQ or the multiple signals can propagate within the SEQ. This style of implementation does not make very good use of hardware until or unit, since each unit is an active for the fraction of the total clock cycle. So this is your SEQ. Now let's see with the help of PPTs what is left in the PPTs. This is done. Now SEQ hardware. As I told you, there are multiple hardware components. These light gray boxes, pre-designed hardware blocks. Example, memories, ALU, this is the memory, this is the ALU, control logic, describing SCL, these are the multiple functions. What is control logic, how we can describe in the SCL. What is white oval, this is the white oval, that is labels for signals. This is darker gray boxes, this is darker gray boxes, this is light gray boxes, that is data assembly, memory, ALU. Darker gray boxes includes control logic, describes in SCL. White oval includes label for signals. This is the white oval that is used for label for signals. Thick lines, these are the thick lines, that is 32-bit for addresses. Thin lines, there are 2 lines, thick lines and the thin line. This is thin line, this is your thick line. That is dark line, that is used for 32-bit value. Thin line is used for 4 to 8-bit values. There is a dotted line also. This is the dotted line that is stored for that is used for 1-bit values. So these are the multiple representation for the SEQ. Then as I discussed with the help of book, that is what is fetch cycle or what is fetch logic. This is the fetch logic. PC increment, instruction memory, split, align, PC, Predefined blocks are PC, register containing PCs, instruction memory, that is read the 6 bytes, PC to PC plus 5 means incrementing the values. Then split into the multiple parts, that is dividing the instruction into the I code and the IPER, align the values for the RA, RB and the val C. This is your fetch cycle. Fetch logic, this is fetch logic, this is also a fetch logic. Next is your ISTR, need register ID, need values. Then fetch control logic. Next is your fetch control logic, that is how to fetch the data by using the controls. This is your C syntax, this is your C programs, this is again the fetch logic. Next is your decode logic. As I told you, there are two requirements. One is register file, one is control logic. Register files are used for read, write, for using the addresses. Control logics are SRCA, SRCB, that is source, destination. Source are used for reading the port addresses. Destination are used for writing the port addresses. This is read, this is write, addresses. So these are the two fetch and the decode logic, and we are write and the decode, ALU, that is execute, I have discussed already with that before. So that's all for today's session. Now if you have any doubt, then please text the doubt, but before that let's take a quick review what we have covered in the today's class. This is your book, this is also finished. So let's take a quick review what we have covered in the today's class. In today's class, we have continued with the processor architecture, that is chapter number 4. Our main topic is that sequential Y86 implementation. That is how we implement, or the how computer implement Y86 sequentially. That is sequential Y86 implementation. There are three topics, there are three parts of Y86 implementation. First one, introduction, that is introduction to the Y86. Then what is Y86 ISA, that is instruction set architecture. Then Y86 implementation, that is how to implement Y86. First one is introduction. We have discussed what is Y86, that is an enhanced version, or that is a subset of the or the new version of the IA32. That contains 8 general purpose 32-bit registers, 1 PC, 3 condition codes, 12 types of instructions. Then next one is your Y86 ISA, that is Y86 instruction set architecture. These are the registers that we use, that is 8 registers from 0 to 7, that contains 2 par 32 bits. Then we also discussed about the instruction types. One instruction type is memory transfer, or the register to memory transfer. These are the instructions. This is one instruction, this is one instruction. Then these are the multiple another instruction we have discussed, that is RR move well, IR move well. These are the arithmetic instructions like add, subtract, AND, XOR, multiply, divide, modulus operator. Then these are the multiple new instruction type like unconditional jump or the conditional jump. This is unconditional jump, this is your conditional jump. These are the multiple conditional movement. Till now we have discussed about the movement, but this is the movement based on the conditions. This is your runtime stack, that is how we can implement the Y86, or how the elements of Y86 is covered or is stored in the stack, that is LIFO, last in first out. This is local data, argument 1, argument 2, argument 3, return addresses. These are the instruction types, how to use the procedure code, or how to call the procedure, and how to return the values. This is the example which we have discussed. This is a C example. We are using the arrays, or we are defining the arrays for storing the values, or for showing the functions. We are also using, or we have also used the pointer for storing the array variable, or for storing the addresses of the array variable. This is how to compile to the assembly by GCC 4.4.3. This is the function, how to process. Then next topic is how to implement the Y86, that is Y86 implementation. In this we have discussed what are the requirements of the Y86, that is CPU, registers, memory, and the combinational logic, and how to describe the combinational or combinatorial logic that is used by the or that is defined by the SCL. Then we also discuss how to divide or what are the methods or what is the division of the instruction execution that is divided into 6 stages, that is fetch, decode, execute, memory, write back, PC, update. This is the example for fetch, decode, execute, memory, write back, PC update. These are the implementation details. That is how to use memory, read-write register file, read-write stage register, different Y86 CPU. This is your SEQ hardware. Then we have discussed about the fetch logic and then decode logic. So that's all for today's session. Now, if you have any doubts, then please text the doubt and I will answer you. In the tomorrow's session, that is tomorrow's class, I will discuss your next topic, that is pipelining. So that's all for today's session. Thank you everyone for listening carefully. Thank you very much. Please text the doubts if you have any doubts.